Today we will design a plasmid that lets yeast secrete insulin, and for that we chose this backbone because it already contains the alpha secretion signal, and the alpha secretion signal basically, if it's attached to a protein, the yeast will
excrete the protein or the protein of choice in the cytoplasm or in the environment,
to the extracellular space. Yeah.
Right. It's a mating factor. It's a mating factor designed for two haploid yeast cells to mate and then to fuse into a mature yeast cell. Right.
Yeah. So first of all, this plasmid does not contain any sequence that will lead to the yeast holding on to it, except the ampicillin resistance gene. But if you add the 2 mu ori from another plasmid, the plasmid will be episomally expressed. That means, like, if the yeast divides, it will also take this plasmid with it and it won't be destroyed, basically. So that's desirable. So what we will do...
Basically, a stable expression would be 20 to 30 copies of the plasmid in one yeast cell.
Yeah.
Normally.
Yeah. So what we're going to do is a Gibson assembly. Yeah. Create new assembly, Gibson.
So basically, we are now using Gibson assembly to assemble or like to clone a certain sequence from our second plasmid into our first plasmid. So we have a stable expression in our first plasmid, yeast plasmid.
Set fragment. Now that's the backbone, and we will want to insert this part into the backbone.
Did you invert the selection?
I think so. We will see if it works. Create. And I think it worked, right?
Yeah, it worked.
Okay, so we basically got the same plasmid that we started from, which was the PPIC 9 plasmid, and we added the 2 mu ori from the PRS423 plasmid. So now this plasmid would be stably expressed in yeast. And now we want to add the insulin sequence, so that's why we'll go to uniprot, which is like the protein.
A database for protein sequences.
Yeah. And we will scroll down. I mean, here you can see the structural parts of the insulin protein, and here you can see the amino acid sequence. Now,
Basically, insulin contains 3 certain chain protein sequences: the alpha, the beta, or like the A sequence, the B sequence, and the C sequence. and the correlation or the relationship between the A and C sequence is very important for effectivity of insulin and the longevity and plasma half-life of the protein sequence when it will be administered to a person.
So now we
And
have,
we will also
yeah.
And we will also use cleavage sites to cut the mating factor, which we will use for excreting the protein into the extracellular space. We will later need to cut it off, like we also need to cut off the purification tag later on, which contains like a 10 his sequence, which has a high affinity to bind to nickel ions.
Yeah, and now we have the insulin amino acid sequence, and we will back translate it into bases. So we will, as an organism, the optimal organism would be Pichia pastoris, because the PPIC9 plasmid, which we started from as a backbone, it is derived from a native Pichia pastoris plasmid. All those other things are not really important for us right now. Save as new sequence. Right. Now we have the sequence. Now we will translate it back, and then we will need to add a stop codon in order for the translation to stop. Create translation forward. And TTA should work. Oh.
Right. Try TGA.
Or TAA? Oh, okay.
TGA.
Okay, yeah. So now we will take this sequence. Well, I mean, we can add it with using digestion and ligation, right?
Yeah, basically.
So now we will look at the cut sites right here and choose which ones are the best for us. I think
maybe go in sequence view.
We could use E. coli and not I, yeah. So we will look what the cut site is for E. coli and paste that to the beginning of the.
First, we should check if we have only one cut site.
True.
Which is E. coli.
True. Oh, and we should have checked that for the translation too. But now we already started. So it cuts one time, it cuts one time here. So that's
Perfect.
good, because you only wanted to cut on the side where you want to add something, because if it cuts at more sides of the plasmid, you don't really have control what the end product is going to be. Right, okay, so now we are going to look at the translation and look whether the translation contains an equal RI or a not I. So we will. No, it does not contain any cut site for the equal RI. That is good, so we will be able to use that cut site, and it also does not contain not I, so we can also use that as a cut site in the plasmid without any problems. Okay, now okay, we will yeah, we will look at the sequence that is needed for EQRI cutting and copy it from here and basically paste it in front of the insulin sequence.
Let me send you the cleavage sites.
I mean, I already got them. No.
Oh, okay.
They are conveniently marked by Benchling. So
no, your cleavage sites.
Oh, the protein cleavage sites for later.
Right.
Okay. Yeah, the idea basically is that we want to add a 10 his tag to the end of the insulin protein, because if you use a his tag, it will be easier to retrieve the end product of the recombinant protein, basically, because his tags bind well to nickel ions, and that's why his tags are used in conjunction with nickel salts in order to retrieve recombinant proteins from bioreactors. But we don't really want to inject a protein that contains 6 or 10 more amino acids in the end, so we will add a protease cleaving site in the amino acid sequence. Yeah, wait a second.
The big problem really lies in the fact that 6 or 10 his amino acids will certainly change the solubility and the plasma half-life of the insulin product in the end. So you always want to make sure, if you have more than 6 his tags, that you cut them off with a cleavage tag before using it.
Is that right? The translation?
Right.
Okay, yeah.
For these 1K.
So now we will look up.
Wait,
histidine was H, right?
Right. I already sent you the sequence.
Oh, okay, nice. So what we basically will add now is the 10 his tag. Which is like the amino acid histidine,
but for the end of the sequence, maybe we should use the backward cleavage site, because we want to cut in the different direction than forward.
Okay.
So K and then 4 times the D.
Yeah. Yeah. How was the enzyme called, the protease called that you searched?
Enterokinase cleavage enzyme.
So that's basically going to be a protease which will cut right here. So the insulin product is not changed and is perfect, quote unquote. but the 6-his tag, we will be able to remove the 6-his tag from the final end product. And before that, there will be the alpha secretion signal, but oh, we need to be careful.
But everything will be fine, because like 10 or 11 amino acids after the alpha or the alpha factor will end, it still will be translated.
Yeah, true. No. I just wanted to look whether with the cut site there will whether there would be the possibility of a frame shift occurring, but no, that's not a problem, I think.
Right.
It seems to be multiples of 3, so we're good.
Otherwise, you should be warned by Benchling in the cloning process also.
Yeah. Okay. So now we will do another assembly in order to get the insulin into that plasmid backbone we prepared.
First we started with Gibson Assembly, because we could only use Gibson Assembly as a cloning method. But now restriction site cloning seems to be the best solution, because we have limited space and we have already an alpha factor secretion signal, which is already in frame with transcription. So to use restriction cloning is the only and the best solution in this scenario.
Shift select.
Right.
Did it work?
First select the restriction site, and the second one with shift left click.
Okay. Now I get it. Set
And
from
then
selection. Okay. But I'm worried that it will, I think.
No, you see, it's selected.
But reverse.
But you need to invert the selection.
Yeah, I reversed the orientation here. I think that will be fine, right? No.
No, like it will use the direction which you choose, because when you first, it's your first restriction site you marked, and then the second one it will be the direction you marked it.
But it says 13 base pairs, so I think I will try again.
But should be perfectly fine.
Okay. Okay, now we will go to the insert, which is the insulin.
I think it's just shown in a weird way.
Okay.
It's fine.
2 errors and 0 warnings. It's fine. I think we will.
The sticky N does not match.
No, I reversed the selection. Now it works, I think. I think it should work. I mean, we can.
Try it one time.
I'm pretty sure that's not what we wanted. So basically it's just the other way around. So I will delete this again. I can't really delete it here, so I will move it. I mean, I will just try again and delete it later.
Wait.
Okay. Try number 2. stored.
Wait, I try to
Backbone.
in Benchling.
Invert selection, set from selection. Yeah, I think it's right now because it says 9.1 kilobases, which seems more right than.
So now it's properly in the invert selection.
Yeah.
Right.
Set from selection. And now it also has 0 errors and 0 warnings, so I think that looks right. Assemble. Yeah. Yes. No, it didn't work. Why is that? Oh, yeah, I think it worked. It just did not. It does not have an annotation, right? I think we can take a look.
Okay. Ah, you don't annotate it before, right?
Yeah, I didn't. Yeah.
Okay.
I hadn't annotated it yet. So first of all, we will create a translation to be sure. So now you can see that it's the same sequence. It just, yeah, we just basically haven't annotated it yet. So now we will annotate it.
Maybe also try to create an like an AA sequence from the beginning of the alpha factor to the end of the insulin sequence.
Yeah, I will. Tag, save annotation. Okay, a very descriptive annotation. And now I will add the translation of the alpha secretion factor too. Create. Oh, no.
First, you can use the translation, right?
Yeah. I think it seamlessly seems to.
It all should be in line,
work.
right?
Yeah. Yeah. I mean, you will possibly take a few amino acids of the alpha secretion tag, probably 4 or something, but yeah, the alpha secretion tag will also be we will also be able to cleave that off using another protease. Right. So that seems to be the final product. And now we will maybe go through the other sequence elements. The ORI is for propagation in normal bacteria. The ampicillin resistance is basically a resistance to the antibiotic called ampicillin. And the AOX1 promoter is a promoter that works in yeast. Right. And
it's like the this promoter is also well regulated by methanol.
Yeah, methanol. Right.
Methanol alcohol.
And the PPHIS4 is like the enzyme the Pichia pastoris needs to produce histidine, and you will in genetic engineering probably work with a Pichia pastoris strain which will not be able to synthesize histidine on their own. So when you add this plasmid, they will be able to survive. If they don't get this plasmid, they won't be able to survive. And by doing this, you basically ensure that only those yeasts survive that are genetically modified by you. Yeah. Right, and MCS stands for multiple cloning site, which is like a region of a plasmid which contains lots of cleavage sites for nucleases. So oftentimes it's the optimal point of a plasmid for you to add your gene of interest. Yeah.
And to add something to the ampicillin resistance. The ampicillin resistance is also not only a resistance to ampicillin, but also to other antibiotics which come from the same family or works the same way, like all beta-lactam antibiotics. Like, for example, penicillin, amoxicillin, and like 10 or 20 other antibiotics that all work in the same way.
Yeah, I mean, I can show ampicillin. Yeah.
They all work in a similar way, or they all affect the same pathway in the bacteria.
Yeah, and by adding a beta-lactamase, the bacteria will basically be able to destroy this molecule, and so they won't be harmed by the antibiotic anymore. Okay, I think we are
done.
We are done for today. Bye bye. Okay, quick rework. I added another enterokinase cleavage site at the beginning of the sequence in order so that the processing is easier. And the enterokinase is a protease that will cleave after exactly this sequence, this amino acid sequence after the lysine, and lysine is encoded as a K. And one at the front, at the beginning of the insulin, and one on the end, but before the his tag, so that we will have a insulin product that is free of any other amino acids, so that it won't be dangerous and basically will be a perfect insulin product. Yeah, here you can read this too.